time independent, then it should be very clear that you get more than this. So suppose if h is independent of time, then if I have any critical point of h, well, clearly this prescription tells me that the Hamiltonian vector field vanishes there, because dh is 0 there, and so x sub h is also 0 there. And because I said it's independent of time, that this is true for all t, so I'm doing the flow of a vector field, and it's stationary at this particular point. So obviously the flow doesn't move the point. Okay, so apparently, so in this case, well, so the number of fixed points of the time one map is at least the number of critical points of h, right? Because this argument shows that every critical point is in fact a fixed point, and conceivably in this case there could be more. It could happen that this now time independent vector field, because h is independent of time, could have non-trivial periodic orbits, but at the very least it has one for every critical point. Okay, so that's sort of a trivial observation, and by itself one wouldn't necessarily think that there would be a general pattern here. And by the way, notice that. So I claim that this is better than this. Why? Because, well, Morse theory teaches us that there are at least as many critical points as the sum of the Bethe numbers, because you can make a cell complex for the manifold out of with one cell per critical point of the function. So, and by the way, the non-degeneracy here would imply that that h would be a Morse function. But the second case that Arnold also noticed is, suppose this flow stays reasonably close to the identity in, say, C1 topology. Okay, well, so I claim that one can get a similar estimate here. So why is that? Well, consider m cross m. So this has the diagonal in it, and it also has the graph of well, for any t, it has the graph of VHT. So there's by Weinstein's theorem, there's a neighborhood U of the diagonal in M cross M, and a symplectomorphism let's say phi going from U to phi of U, which is a neighborhood of the zero section in the cotangent plane. So this map takes the diagonal, well, I guess, and phi of the diagonal is zero section. So this takes the diagonal to the zero section, and it takes the graphs of these diffeomorphisms to, well, some sort of submanifold. But because I said that VHT was C1 close to the identity, this blue submanifold is going to be C1 close to this white submanifold, which is the zero section. So as a result, this is the graph of some one form, or it's the image of a one form. So phi of graph of VHT is the image of a one form. And, well, it's an exercise to show that in order for it to be the case, okay, so first of all, these VHTs, which are defined on M, give me a Hamiltonian isotopy which takes, which moves the diagonal to these graphs, just by having it be trivial on the first factor and VHT on the second factor. And so, by the naturality of Hamiltonianness, I get an isotopy from the zero section in the cotangent bundle through these images of forms. And it's a Hamiltonian isotopy. And it's an exercise to show that the only forms that arise as isotopies, as Hamiltonian isotopies of the zero section in the cotangent bundle, are graphs of exact one forms. Okay, so these one forms are exact. Let's say dft or something, because VHT is Hamiltonian. The point being that if the form, or one way of seeing this, briefly, is that if the form was not exact, there would be some curve that it integrates non-trivially. There's some simple closed curve that it integrates non-trivially over. And if you sort of move that simple closed curve along the isotopy, it sweeps out a cylinder. And in order for the isotopy to be Hamiltonian, the form has to integrate trivially over the cylinder. And by virtue of what the form is, that can't happen if these forms were to integrate well, so that integral of the form on the cotangent bundle over the cylinder would actually be equal to the integral of this form over the original curve. Okay, so with it said, so how many fixed points are there? Well, there are as many fixed points as there are intersections between this blue submanifold and this white submanifold, which is to say there are as many fixed points as there are zeros of this form. So the number of fixed points of VH1 is the number of zeros of, so df1 inverse of 0, which is an odd way of saying the number of critical points of f1. Okay, so in each of these two special cases, two pretty conceptually independent special cases, one where the Hamiltonian is time independent and another where the Hamiltonian path stays C1 close to the identity, we got something significantly better than this Lefschetz estimate. We found that the number of fixed points has to be at least equal to, in one case exactly equal to the number of fixed points of a function, or the number of critical points of a function. Okay, and so my impression is that these two special cases together are what motivated Arnold to make a famous conjecture. So the Arnold conjecture asserted that assuming, well, there's a version for the degenerate case, but I'll just discuss the non-degenerate one. So assuming all fixed points of VH1 are non-degenerate, the number of fixed points of VH1 is at least the minimal number of possible critical points, or f from M to R as a Morse function. And this Morse condition corresponds to this non-degeneracy condition here. If analogously, one could drop this condition and say that this should be at least equal to the minimal number of critical points of any function. So, to the best of my knowledge, this, as written, is pretty much entirely unresolved, at least for general M. The game that one can, so what one can do instead, so these two special cases, this works out in these two special cases, but in general, the best that one can do, and this is pretty good though, is one can pick a number that this is bounded below by, and show that this is also bounded below by that number. So, as I was mentioning, the minimal number of critical points of a Morse function is bounded below by the sum of the Betti numbers. Of the manifold, because of the fact that using a Morse function one can construct a cell complex with a manifold that with one cell per critical point of the Morse function. Okay, and obviously this estimate is significantly better than this one. And of course, if I decided I wasn't just interested in Hamiltonian symplectic morphisms, I was interested in more general symplectic morphisms that are isotopic to the identity, just thinking about the torus shows that this would be completely false, because you can rotate the torus and it doesn't have any fixed points. But what Arnold speculated and was right about was that in this more general setting, or in this more specific setting, one can get a better lower bound. And so as of over 10 years ago now, the conjecture in this form has been proven. And I'll try to briefly indicate how that works. Okay, so what Hamiltonian Floer homology is, or Hamiltonian Floer theory, let's say that. So it's an infinite dimensional version of Morse theory well, it will be a theme of the two lectures to follow that it does much more than what I'm about to say, but what it was designed to do was to prove this estimate, that the number of fixed points of phi is at least the sum of the Betti numbers. So it's an infinite dimensional version of Morse theory. So to do Morse theory, you need to have a manifold that you're working on. So maybe in simple cases, here's the manifold that one works on. The manifold is the contractible loop space of the symplectic manifold that you start with. So this is the space of loops for gamma from R mod z to m, so that gamma is contractible. And so note that if gamma dot of t is, so if gamma is a loop, and if it is the case that gamma dot of t is xht of gamma of t, so remember the point is that the flow is the flow of these vector fields, then evidently gamma of 0 is a fixed point of the time one map. So finding elements of this which satisfy this equation is tantamount to finding fixed points. Now, if I were to drop the 0 and just talk about arbitrary loops, then sort of this would be if and only if. But it turns out that at least from a homological standpoint, this will detect sort of everything that there is to detect by the theory. So the proposal is to use Morse theory, or some infinite dimensional analog of Morse theory, to detect loops which satisfy this equation. Well, so this holds if and only if for every vector field xi along gamma, or put another way, every tangent vector to the contractible loop space based at gamma, so a tangent vector to the contractible loop space based at a curve would be a vector field along the curve. it should be the case that the integral from 0 to 1 of omega of gamma dot of t minus xht of gamma of t. So this gives me one vector. If I pair it with this arbitrary other vector, I should get 0. So clearly the downward implication holds, and you can use cutoff functions in a straightforward way to show the upward version, or to show the upward half. So this should be 0. Or I can write this in a slightly different way. This is the, I'll write it as minus the integral from 0 to 1 of omega of c gamma dot of t dt plus the integral from 0 to 1 of h, dh t of gamma of t. So I guess I've erased my sign conventions for Hamiltonian vector fields, but I did set the signs up so that x of h would include into omega as minus x of h, or as minus dh. Okay, so this here, let's call this fractor a sub h of gamma of c. So I've defined a one form, fractor a sub h, which is a one form on the contractible loop space.
Can you go through again how to think of C tangent vector to the loop space, and you have C of t?
Yeah. So what is a tangent vector to the loop space? A tangent vector at a given loop to the loop space. I submit that that should be thought of as a vector field along the loop. Right. So the way to move gamma is to pick a tangent vector at every time, and so that this is these are sections of gamma star of Tn, if you want to be formal about it. Okay, so in other words, to look for fixed points, at least with contractible orbits, is to look for zeros of this one form on the contractible loop space. Now, if this one form were an exact one form, that were d of something, looking for zeros of a one form would of course mean looking for critical points of that function that it's d of. This is, in the general situation, this is a closed form. It is not generally an exact form, but of course you can make an exact form by pulling back to a larger space. So the one form, a sub h, becomes exact after lifting to a suitable cover. So the deck transformation group of this cover we'll call gamma. So what this will be is it will be pi 2 of the manifold modulo the kernel of the evaluation map induced by omega. So in other words, given a sphere, integrate omega over it. That's a homomorphism. Intersect the kernel of C1. Acting on the sphere. So I could have just modded out by this, and then I still would have gotten a single valued primitive for this. The point of this is that it will eventually allow me to z grade the complex. Okay, so this deck transformation group will act on, and this will be the deck transformation of a group of a cover, which I'll call L naught m tilde. So this cover will consist of equivalence classes of pairs gamma u, where, well, again, gamma is a contractible loop. U is a null homotopy of the loop. And two such are equivalent So gamma u is equivalent, or is the same as gamma prime u prime if, well, I need the loops to be the same, and I'll want, consistently with what I've defined here, I'll want omega to evaluate trivially on, so this here, so I have a loop gamma and a null homotopy u of that loop. If I have another null homotopy u prime of that loop, I get a sphere, and this notation says glue one disk u to the other disk u prime orientation reversingly along their boundary, so that gives you a sphere. So that gives you a sphere, and you can integrate omega over it. And again, in order to make the grading well defined, I'll also ask the first term has to vanish. Okay, and so the claim is that once I lift to a cover, this has a primitive, so I can write it down. So set AH of gamma u equal to minus the integral over d2 of gamma of the symplectic form over this capping disk for the loop, plus the integral of h along the boundary. And so when you try to differentiate this, so I mean we're just lifting to a cover, so the tangent space is still vector fields along the loop, and when you differentiate this part in the direction of a vector field C, you easily see you get this, and when you differentiate this part along a vector field C, you get that. I'm sorry. Yeah. Okay, so this is, okay, so pi 2 of m's a group. On that group I have two homomorphisms. So this is the kernel of the homomorphism on pi 2 induced by integrating omega over spheres.
What's the subscript?
Intersect.
Wait, isn't there some sort of subscript? Like
Comma and dot, yes. Okay, so sorry for the suboptimal handwriting. Okay, and then and again, it is the case that DAH is, I guess the way to say it is DAH on at gamma comma u is AH at gamma, since the tangent spaces are identified. Okay, so finding zeros of this one form, or finding zeros of the pullback of the one form to the cover, at least, is the same as finding critical points of this function. Okay. Okay, so this has critical points. Precisely those gamma u with the property that, well, with the property that gamma of 0, or with the property that gamma dot of t is xht of gamma of t. And so, well, so to relate, so what was the original problem? The problem was to somehow count the gammas that have this property. Well, so there's an action of this capital gamma on these that I get by gluing spheres to the disk, and so in principle this will have infinitely many critical points no matter what, because if I have one I can always just glue a sphere on and I get another one. But the point is that we'll have one capital gammas it'll have one capital gamma orbit per fixed point that I'm interested in. And so ultimately what one would want to do is count up the number of capital gamma orbits in this critical point set. Okay, so so what is Floer homology? Floer homology, or Hamiltonian Floer homology, is going to be basically Morse homology for this function on this space. Or really, I should say Morse-Novikov homology, because of the complications arising from the cover. So, okay, so what is Morse homology? I hope most of us have seen this at some point before. So what are we supposed to do? So the generators loosely should correspond to critical points of the function. So an arbitrary element of the complex ought to be some sort of formal sum of critical points. And, well, I'm taking homology, so I need a boundary operator. So the boundary operator so what's it supposed to do? It's supposed to it should count negative gradient flow lines. In this sort of standard sense that likely most people in this room have seen before. So, well, so in order to tell you what the boundary operator is, I just have to tell you what it does to the generators of the complex. So if this is one generator and if it has certain negative gradient flow lines issuing from it, say, going down to Q1, Q2, Q3, then in this picture, what I would say is that the boundary of P should have, in order to say what the boundary of P is, I should follow the various gradient flow lines down and record where they land. So I follow this one down and I write down a Q1, and then I follow this one down and I write down a Q2, and then I follow, well, I see two of these, and I guess really it would depend on how various signs work out, but if the signs were both positive, I would get a Q3. Okay, but so how does this work in practice? And I mean, you can't just throw out an infinite dimensional manifold and say I want to do Morse homology on it. You need to know something about how the actual gradient flow lines and critical points work. And in fact, I mean, the naive guess as to what you get when you might do this might be you'd get the homology of the loop space, and that's not what you get. You get the homology of M. So clearly this isn't completely trivial. Okay, but again, how does this work in practice? So the first thing about this is I said negative gradient flow lines. So of course, in order to say what the gradient flow is, I need a metric. Well, there's a standard way of doing that, of course. So the metric on lambda M tilde. So what I can do to make a metric on this space is I can choose a family JT of omega compatible almost complex structures. And then, well, so as we discussed, what is a tangent vector to, well, either this or this? It's a vector field along the curve, so I can simply integrate, well, the metric pairing of these two vector fields at any given time. So omega of CT, comma, JT, zeta of t. Okay, and well, if you then look at this formula for what the derivative of, what the exterior derivative of the action functional is, you can pretty quickly read off what the gradient is. So the gradient of AH at gamma well, so it's supposed to be a vector field, so it's supposed to be a vector field along gamma. So let's evaluate it at any given time, and it's supposed to be somehow the direction of steepest descent of, or the c which makes this as large as possible, in essence, for any given, or the c which makes this as large as possible and has the same magnitude as that. And the way to do that is to have it be jt times gamma dot of t minus x of h. Okay, so that's what the gradient vector field is, and so I'm supposed to count negative gradient flow lines. In other words, I'm supposed to count R parameterized families of gammas, which satisfy the equation d gamma ds is equal to d gamma ds plus this is 0. Well, so negative gradient flow lines well, so they're supposed to be R parameterized paths of loops. So that's another way of saying cylinders. Domain R across R mod Z to M. So at time s, this is a path of loops such that at time s the relevant path is u of s comma dot. So it should be the case that du ds plus the gradient, because I'm doing negative gradient flow line, so I should, if I wanted it on this side of the equation, I should add it, plus jt du dt minus xht of u of st is equal to 0. Okay, and once we write down this equation, well, at least nowadays we know to be optimistic, because this is an elliptic partial differential equation, and it has nice compactness properties, for example, and so one can hope to get a reasonable theory. So what are some facts about solutions to this equation? So first of all, this first fact basically arises from the fact that this is the negative gradient flow equation of the function that I wrote down. So if I have a solution to this, or actually this is maybe even more basic than this. If I have a solution to this, and if it has finite energy, so let's call the energy of a solution to, or I guess the energy of any, yeah, okay, let's say the energy of a solution to this. Just take basically the Dirichlet norm of the squared Dirichlet norm of the function. So if the integral of du ds, and of course this is, by using the equation, this is the same as a half times the integral of du ds squared plus mod du dt minus x to h squared. So if this is finite, then, well, the only way this energy can be finite, although it's defined on an infinite cylinder, is if this is getting small, if this integrand is getting small as s is going to infinity. And I maintain the assumption throughout that phi sub h is non-degenerate. And so the only way this gets small, at least under this non-degeneracy hypothesis, so that somehow one has exponential decay results and so on. The only way that this gets small is if u converges to a critical point as s goes to plus or minus infinity. So there are some gammas, gamma plus minus, let's say, in L naught of m, so that gamma dot is x sub h, and as s goes to plus or minus infinity, the cylinder converges to these gammas. Okay, so we have a gamma minus and a gamma plus, and the only way that this u can have finite energy is if it somehow interpolates between them, and I say converges, and because of the non-degeneracy hypothesis, that you can pretty much make this in practically any sense you want. There are actually statements to the effect that it converges exponentially. Okay, so this is good in that it says the gradient flow lines actually converge at their end. Finite energy gradient flow lines actually converge at their endpoints to critical points. So the second basic fact is that, again, arising from the fact that what we have here is the negative gradient flow equation. So given this convergence behavior, well, so this is a statement about loops. So in order to make it a statement in this cover, I need to introduce these capping disks. So maybe I cap gamma. I suppose I could choose any disk I want to cap off gamma minus.
Can I just make one comment about this energy?
Yeah.
Just for the student. I think that is correct. Real energy for that equation should be the second line, right?
Well, but don't you agree that these are equal?
Yeah, they're equal, but equal solutions, right?
Yeah. Okay. If you solve star, yes. But, So but you're exactly right that if I wanted to think about U's that don't solve star, then this would be the right thing to look at. Okay, so.
Mario, is it possible that there are solutions that converge on either end but don't have finite energy?
No, I don't think there. I think that once you have, at least under this non-degeneracy hypothesis, but basically once you have convergence, once you have like uniform convergence, you get exponential convergence. Okay, so take any disk I want to cap off gamma minus. Now, if I have this cylinder, that basically gives me a disk with which to cap off gamma plus. Namely, follow the cylinder back to gamma minus, and then finish it off with this disk that I use to cap off gamma minus. So I'll denote this by. I have to decide which one I want first. Let's say U minus. Connect some U. So this is a capping disk for gamma minus. This whole thing is a capping disk for gamma plus. So that in this case, this U would be regarded as a flow line from this specific critical point to this specific critical point with this distinguished capping disk. And because of the gradient flow equation, one gets the important estimate that the difference in the values of the function at these two critical points is the energy. And the order is right here because this is a negative gradient flow line, so the function should decrease along its gradient flow lines. And in particular, this is always positive, which will play a role in things we say later. So the third fact, which is basically Gromov compactness, so has to be a little bit careful about how one formulates it in general, but basically subject to any given energy bound, the space of solutions of this will be compact modulo a certain standard degeneration. So for any real C, the space of U, so that U solves the gradient flow equation, and the energy is at most C. This is compact modulo, well, two types of degeneration, so modulo bubbling, and broken trajectories. And I won't attempt to state these, to say what these are precisely, but I'll draw pictures that hopefully convey the basic idea. So what is bubbling? So maybe one has a sequence of gradient flow cylinders that starts to look like this, and then what they degenerate into is a gradient flow cylinder with a bubble or possibly several bubbles coming off of it. So this would be a holomorphic sphere. And again, there could be lots of these. There could be one over here and another one over here and so on. Okay, so we don't like this. What we do like, so that's convergence, that's compactness modulo bubbling. The broken trajectory phenomenon is that maybe I have a sequence that starts getting dangerously close at, say, time s equals 0 to some other orbit, and then what it can degenerate to is sort of a tree that stops at this orbit. Or so the first part here is just, instead of being so this is a unit. This is one cylinder defined on r cross s1. This is a cylinder defined on r cross s1 that is asymptotic to an orbit in the middle here, and this is another cylinder that's asymptotic to the same orbit. Okay, and so we like this. This is what's going to make the theory work. It's going to it's what causes d squared to be 0 and so on. So this is a genuine problem, and it took a lot of work by a number of people, some of whom are in this room, to figure out how to deal with this issue. But the reason why it should be okay morally is that this is a codimension 2 phenomenon. So at least if the dimensions of all the moduli spaces are correct, this is a codimension 2 phenomenon. And so it can be avoided by a generic choice of H and J when at least under some topological hypothesis on the manifold, called semi-positivity, or more complicatedly, it can be avoided using multi-valued abstract perturbations. In general. And so somehow this ends up not really it's complicated to make these arguments, but it ends up not complicating the issue in a fundamental way. And so the way of doing this is you independently to Fukaya, Ono, and Liu Chen. Okay, but this is a serious technical problem that can be addressed. This is sort of a fundamental part of the story.
Can be avoided as far as the definition of the boundary operator. That problem can be avoided as long as as far as the D bar is concerned, the definition of a boundary node is concerned.
Right. Yeah. So I mean, in order to make the arguments, one only needs to work in one-dimensional moduli spaces, and so I guess I haven't written down the Lauder operator yet, but okay. And the last fact is that so generically, for some appropriate definition of the term, solutions to the gradient flow equation again with the asymptotics that I indicated form a smooth manifold, or a manifold of dimension okay, so the manifold will be named M of gamma minus U minus gamma plus U plus, and it will have a particular dimension, the difference of the Conley gender indices. So since I've incorporated these capping disks into the story, I can pull back the tangent bundle over these capping disks and trivialize it, and then looking at the linearization of the diffeomorphisms along the perimeter of the along the path, I get a path of symplectic matrices, and this Conley gender index is some sort of winding number of that path. And okay, so I guess I said manifold. I guess in this abstract perturbation situation, you might need something more complicated, like a weighted branched orbifold or something like that. But it still works out. Okay, so using these facts, one can write down algebraically what one needs to do. So, okay, so let's first address the sort of easier case where M is symplectically aspherical.
This is information.
Yeah.
So that statement, right?
Uh-huh.
Shouldn't be here, right? That can be this bubbling can be avoided for generic choice of H and J.
Okay.
Here in this statement 4. In dimension.
Yeah. Okay. So, right. So it can be. Right, okay. I guess the right statement would be that the configurations with bubbles form a codimension 2 set within this.
So this can be avoided when the dimension of this is 0 and
Okay. So it can be dealt with. How about that? It's something that happens, but it doesn't mess things up. Dealt with. Okay, so let's assume, for simplicity, that this is symplectically aspherical. So, in other words, that omega and C1 vanish on pi 2. Okay, so in this case, all that stuff that I was saying about covering spaces doesn't enter into the situation. So then, that covering space of the contractible loop space actually is the contractible loop space, and we just have. So remember, our function had, well, a sort of deck transformation group orbits worth of critical points for every fixed point of phi, but because there is no deck transformation group, it just has one critical point for each fixed point of phi. So then set so just take the, I guess I'll retain the notation gamma u, even though the u isn't really relevant. So just take the free abelian group over the critical points with well, so if I want the kth graded group, I'll ask the Conley gender index to be k. So this is a free abelian group with one generator for every, well, for all of the fixed points that I'm interested in, at least as I vary k. And so to say what the boundary operator is, I need to say what it does to each generator, and so I guess d of gamma minus u minus will be the sum over all gamma plus u plus with index 1 less. Of, well, that moduli space is one-dimensional, but it has a free R action. Mod out by that free R action, and I get a zero-dimensional submanifold, or I get a zero-dimensional manifold, and count its elements with appropriate sign, which I'm not going to explain how the signs work. But it can be done in an appropriate way. So this is counted with sign. So I'm doing here exactly what I drew here earlier. I'm starting at a generator. I'm looking at the isolated gradient flow lines that issue downward from that generator and recording where they land. And so I guess by virtue of sort of fact 4, this is a finite number for any gamma plus u plus. Okay, so this is finite. Now the reason I wanted this to be symplectically aspherical is so that this would be a finite sum, because there are only finitely many different gamma plus u pluses. Or sorry, I guess this is finite by 3 and 4. So it's zero-dimensional by 4 and it's compact by 3. So this is a finite sum by the asphericity hypothesis. Asphericity. Okay, so this is actually a well-defined element in this group, and well, so the theorem is that. So I guess it's mostly due to Floer. I guess maybe some of the details with Conley gender indices and so on were really worked out by Solomon and Gender. So d squared is 0. So this is sort of the standard story where you have, I guess, corresponding to that picture. So if I want to know what d squared of p, with the matrix element of d of p, d squared of p with r is, well, so that counts configurations like that, consisting of a pair of a gradient flow line from p to some intermediate point q, and then another one from q to r. And the point is that these, sort of a standard argument that if I look at the moduli space of gradient flow lines that just go straight from p to r, they form a one-dimensional submanifold, or they form a one-dimensional manifold, and the boundary of that manifold is precisely what's counted by d squared. So I'll say more about this at some point in the future. I'll say more about why this is, because we'll need why it is in more detail. So the chain complex is, it's a chain complex since d squared is 0. So the chain complex is associated to different choices of pairs consisting of a Hamiltonian and a path of almost complex structures are chain homotopy equivalent. And so in particular, they have the same homology. Okay, so of course that means that in order to evaluate the homology, I just have to pick my favorite Hamiltonian and see how it goes. And, well, so if H is a C2 small Morse function, time independent, and if J is time independent, then what this complex just is the Morse homology of H. So this is, well, this is something that you get just by thinking about H as a function on the smooth manifold and counting gradient flow lines, counting its negative gradient flow lines on the smooth manifold. And this is an equation of chain complexes. So apparently HF star of H is H star of M, because the homology of the Morse complex is just the homology of the manifold. And so by 2, so this is so if H is a C2 small Morse function, but by 2 it's also true for any H. So corollary, for all H, HF star of H is H star of M. So the number of fixed points of pH1. Well, so what is that? That's this complex, because of the asphericity hypothesis, just had one fixed point for every, or I guess actually because of the contractibility assumption, it has one generator for each contractible periodic orbit. So this is at least so if I think about all of the fixed points, well, some of them might have non-contractible orbits, so it's at least equal to the rank of CF star H. And well, if I have a complex whose homology is the homology of the manifold, then obviously the number of generators in that complex has to be at least the sum of the Betty numbers of the manifold. Okay, so this proves the Arnold conjecture for aspherical manifolds. How am I doing on time? 5 minutes? Okay, so I'll try to say what you do to deal with a non-aspherical case. So in the non-aspherical case, remember we have this this covering space and so there, rather than it being the case that there's, so I could try to form this, but then this would have infinitely many generators. It would have, if you like, it would be, I guess one way of saying it is that it would be finitely generated over the group ring of gamma. It would have a gamma orbit's worth of generators for every fixed point that I'm interested in. Okay, so this is the non-aspherical case. Okay, and the main issue to address is that if I define this, so this is, the sum of this formal sum of critical points that I get by that I get by counting elements of zero-dimensional moduli spaces. Well, so each of these individual numbers one can still argue is finite, at least if one deals with bubbling in the appropriate way. But the problem is that this is not a finite sum. Because there are infinitely many different gamma plus u pluses to deal with. So if I try to just copy this, then, well, this would not live in this space. And so it's not, this expression would not live in this group. So one needs to somehow deal with this. Well, looking at what Gromov compactness tells us, it gives us some hint as to how to deal with it. So given gamma minus u minus and some constant, well, so remember I have this expression that says that the energy of any of these gradient flow lines is AH of gamma minus u minus minus AH of gamma plus u plus. And I have compactness, and in particular finiteness, subject to any a priori bound on E of u. So if I bound E of u, then also so u is giving me one thing in this big sum for any u. If I say, well, I'm only going to pay attention to the E of u, the u's that have their energy below a certain amount, then there will only be finitely many such contributions. So if I view this as fixed, so, and I'm just trying to define D of a given generator. So if this is fixed, then this is fixed. And so if I bound this from below, then I bound this from above. So what's the convenient way of formulating this? So I guess what can be said is so there are just finitely many u, or finitely many gamma plus u plus, with AH of them at least C, which contribute to this expression. Gamma u with AH gamma u at least C appear in the sum, so have little a gamma u non-zero. Okay, so I'm forced to deal in general with infinite sums. There are some slightly more general assumptions than asphericity you can impose, like monotonicity, that get you around this, but in any level of generality beyond that, you need you're obliged to deal with infinite sums in the Floer complex. So, well, this may not look so good because I know that this is going to be infinitely generated no matter what, but the point is that this is a finite rank module if I enlarge my ring. So gamma, which I remember is this quotient of pi 2, it acts on well, a general generator by having, say, a pi 2 element act on this pair that consists of a loop and a disk by just gluing the sphere to the disk, and how does that affect things? It changes the action values. One subtracts if one remembers the definition of the action. One needs to subtract the area of the sphere. And as a result of this action, this space of formal infinite sums will be a module over well, a completion of the group ring of gamma, and this is called the Novikov ring. So because of this minus sign, instead of a greater than or equal to. Here I'm going to have a less than or equal to, but other than that, I just take formal sums of, well, to symbolize that I'm dealing with the group ring, I'll exponentiate. So this is A and gamma with a property that for all C, only finitely many A with omega on A less than or equal to C have non-zero coefficients. Okay, and this action of gamma on the generators extends to an action here. And the big theorem, which is work of many people, for Solomon, Ono working alone, and then later generalizing through Kai and Ono together in Liu Tian. So, subject to these definitions, so this is, well, so I guess before I say this, this is the rank is the number of gammas in which satisfy the equation that I want to. And then I can make this definition, and then d squared is 0. Well, it's exactly the same as before. So I guess before this, it's easy to see that d is a homomorphism of modules over this ring. D squared is 0. And then, just like the aspherical situation, if I take the homology, which by definition I'll call HF star of H, this is equal to the homology of the manifold with coefficients in this big ring. And this is independently of H. And just like before, different choices of H give you chain homotopy equivalent complexes. Okay, so the result of this is that the number of fixed points of VH1 which is at least the rank over lambda of the Floer complex is at least the sum of the Betty numbers. Okay, and so this, well, so I guess the Betty numbers with coefficients in this ring, but this is the same as the standard Betty numbers. Okay, so this is, I realize this is rather old news to a lot of people here, but this is an overview of the construction of how this construction works. So, and this was all done over 10 years ago, and so that this tells us that we get this complex which is independent, or whose homology is independent of H, and sort of where we're going after this is, so we've proven this wonderful statement that says that any Hamiltonian diffeomorphism has to have all these fixed points, more fixed points than you would expect from classical topology. So that's a great statement about every Hamiltonian diffeomorphism. But surely not every Hamiltonian diffeomorphism is the same. Surely there are interesting properties enjoyed by some Hamiltonian diffeomorphisms, but not others. Now the homology is apparently independent of the Hamiltonian, so it's not going to tell you something interesting about any properties that are enjoyed by some Hamiltonians and not others. But what we're going to see in the future is that if you look more closely at the chain complex itself, you can see interesting things that are unique to specific Hamiltonians. And so that's sort of where we'll be going in the next two lectures.